Hello all, welcome to my channel. In this video, we will learn about the supervised machine learning. Machine learning, or ML, is a field of artificial intelligence that allows computers to learn patterns from data and make predictions or decisions without being explicitly programmed. Types of machine learning. Supervised learning, we have input-output pairs. Unsupervised learning, no labels why. Reinforcement learning, agent learns by interacting with environment. Supervised machine learning is a type of ML where the model is trained using labeled data. Each input X has a corresponding correct output Y. The goal is to learn a function so that it can predict outputs for new unseen data. In simple words, we give the model examples with answers, and it learns the pattern. Types of supervised learning. There are two main types. Regression. Output is continuous. Example output, price, temperature, salary. Classification. Output is categorical. Example, spam or not spam, disease yes or no. Regression predicts numbers. Classification predicts categories. List of supervised ML algorithms. Linear models. Linear regression. Ridge regression, L2. Lasso regression, L1. Elastic net. Classification. Logistic regression. Softmax regression, also called multinomial logistic. K-nearest neighbors. Support vector machines. Support vector machine, linear SVM. Kernel SVM. Tree-based models. Decision tree regression. Decision tree classification. Bagging methods. Random forest. Probabilistic models. Gaussian naive Bayes. Multinomial naive Bayes. Bernoulli naive Bayes. These are core supervised algorithms every ML engineer should know. Advanced algorithms. Boosting methods. Eta boost. Gradient boosting. XG boost. LightGBM. Cat boost. Histogram gradient boosting. Neural networks. Perceptron. Multilayer perceptron. Deep neural networks. Convolutional neural networks when labeled data is used. Recurrent neural networks. LSTM. GRU. Online learning algorithms. Stochastic gradient, descent classifier or regressor. Passive-aggressive. Ensemble variance. Voting classifier. Stacking. Blending. These are advanced production-level models. Linear regression. A regression algorithm that models a linear relationship between input features and a continuous target variable. It assumes the output is a weighted sum of input features. When to use. Target variable is continuous. Relationship is approximately linear. Dataset is small to medium. Interpretability is important. Why to use. Very simple and fast. Easy to interpret coefficients. Strong baseline model. Linear regression formula. Formula. Y hat equals W transpose X plus B. Meaning of symbols. X is feature vector. Xi is ith feature. W is weight vector. Y is weight for feature I. B is bias or intercept. Y is actual value. Y hat is predicted value. N is number of samples. J of W is cost function. This cost function is usually mean squared error. Ridge regression, L2. Linear regression with L2 penalty to shrink large weights. When to use. Multicollinearity exists. Many correlated features. Overfitting problem. Why to use. reduces model variance, stabilizes coefficients. Formula includes lambda times sum of squared weights. Lambda is regularization strength. Y squared is squared weights penalty. Lasso regression, L1. Linear regression with L1 penalty that forces some weights to 0. When to use? High dimensional data. Need automatic feature selection. Why to use? Create sparse models. Removes irrelevant features. L1 penalty adds some of absolute weights. Logistic regression. A classification algorithm that predicts probability using sigmoid function. When to use? Binary classification. Linearly separable classes. Why to use? Outputs probabilities. Interpretable. Fast and efficient. Logistic regression formula. Formula. P equals 1 divided by 1 plus e power minus. Symbols. Z is linear score. P is predicted probability. E is Euler's constant. Y is actual label 0 or 1. Sigmoid converts linear output into probability between 0 and 1. Softmax regression. Extension of logistic regression for multi-class classification. When to use? Multi-class problems. Mutually exclusive categories. K equals number of classes. WK is weight vector for class K. P of Y equals K given X is probability of class K. Softmax ensures all probabilities sum to 1. K-nearest neighbors, KNN. Non-parametric algorithm that predicts using nearest training samples. When to use? Small datasets. Complex nonlinear decision boundaries. X is new input. X prime is training sample. D is distance. Prediction is based on majority vote or average. Machine. Support vector machine. Classifier that finds hyperplane maximizing margin between classes. When to use? High dimensional data. Clear separation margin. Optimization minimizes norm of W. Norm of W is magnitude of weight vector. Y is class label +1 or -1. Xi is training sample. SVM focuses on support vectors. Decision tree. Recursive splitting model based on impurity reduction. When to use? Nonlinear relationships. Interpretability needed. Pi is probability of class I. Impurity measures include Gini and entropy. Random forest. Ensemble of decision trees using bagging. When to use? Reduce overfitting. Strong baseline for tabular data. T is number of trees. HT of X is prediction of tree T. Final prediction is average or majority vote. Gradient boosting. Sequentially builds trees to reduce previous errors. Update rule. Fm of X equals Fm minus 1 of X plus gamma times Hm of X. Fm is model at stage M. Gamma is learning rate. M is weak learner. Each new tree corrects previous mistakes. XGBoost, extreme gradient boosting. Optimized version of gradient boosting with regularization, parallelization, and missing value handling. When to use? Competitions. Large datasets. High performance needed. Why to use? Controls overfitting. Very fast. Handles sparse data. L is loss function. Omega is regularization term. Fk is individual tree. T is number of leaves. W is leaf weights. Naive Bayes. Probabilistic classifier using Bayes' theorem. Formula. P of y given equals P of x, given y times P of y divided by P of x. P of y given is posterior. P of x given y is likelihood. P of y is prior. P of x is evidence. It assumes conditional independence between features. Thanks for watching.